So it's a great pleasure to welcome Professor Kumar Murty for the last talk of today's conferences, and he will speak about the least prime in a conjugacy class. Please, Professor Murty, it's yours.
Okay, thank you for the introduction. Thank you for the invitation, and I know everybody here must be quite tired, so you won't mind if we even finish early. For me, it's noon, so it's in the middle of the day. But for you, I know it's already 9:30, and you've had lots of talks in the program so far. Firstly, let me wish Balu a very happy 70th birthday. I'm sorry we missed the felicitation, but Balu, we wish you all very well and best wishes and many more years of happiness and health and productive mathematical productivity. So very happy to be part of this conference. So I want to talk about this question, which I've been interested in for many years, but I come back to it now and then and think about it. And recently, one of my students, Ren Zhu, wrote his thesis on a particular case of this problem. So I thought it'd be good to present those results. So the issue is this. So I have a Galois extension of number fields, L over K, and let's say the Galois group is G. And you take a conjugacy set, that just means a subset of the group which is stable under conjugation, or another way of saying it is it's a union of conjugacy classes. Then you take a prime of the base field, K, which is unramified in the top field. So it'll factor in some way. And for every prime Q, let's say, in the top field that divides P in the bottom field, you get an element of the Galois group called the Frobenius automorphism. It's simply the unique lift of the map on the extension of residue fields, which raises elements to the power equal to the size of the residue field of P. That gives you an element in the Galois group, and because of this basic relationship that when you apply a Galois element sigma to a Q, you of course get another prime above P, and the Frobenius just conjugates. Okay, so therefore you get as you vary over the primes that divide P, these things all fit into a conjugacy class, which we call Frobenius sub P, where P is the prime in the lower extension. Okay, so and so this is a conjugacy class. Now let me see if I can. Let's see. Yes. Okay. Good. So then the generalization to the of the prime number theorem in this context is what's called the Chevatoro density theorem, which counts the number of primes of the base field whose norm is less than or equal to x, which are unramified in L and whose Frobenius conjugacy class is contained in this C. Remember, C may not be a conjugacy class; it might be just a conjugacy set, something stable under conjugation. So you count the number of primes where the Frobenius is conjugacy class is contained in this set C, and the Chevatoro density theorem says that it is the Frobenius elements are equidistributed by the discrete measure. So G is a finite group, so it's just distributed by a discrete measure, and so therefore phi sub C of XLK is asymptotic to the size of the conjugacy class divided by the size of the group times the total number of primes of norm less than or equal to x. Okay, so this was known for a long time, but maybe in more recent times, recent being last 50 years, rather than the last 100 years, we have a question has been asked about what is the error term, and moreover, I think it's a kind of modern point of view that the error term has to be effective in all the field constants. So there were various attempts at producing error terms, but sometimes people assumed that certain things were fixed. For example, the base field K is fixed, and so ignored the dependence on the base K, but of course you can't do that. So a totally effective version means it should make explicit the dependence on all of these parameters. So assuming the Riemann hypothesis for the Dedekind zeta function, which is a zeta function of number fields, you get the following kind of error term. You get the main term here as we have here. And then the error term, of course, the x to the half comes from the Riemann hypothesis, that is the zeros of the Dedekind zeta function being on the half line. But then the dependence on the other parameters are like this. There is the size of the conjugacy class that sits here, which is the same as the way it appears here. And then you have a logarithmic term, which is pretty mild. I just will, in general, just write this as script mx. So script m is sort of, in a way, the radical of the discriminant. So this picks up logs of primes dividing the discriminant. And so now, if I have this asymptotic formula, then I can answer the question, when is this positive? Well, when the main, for example, if the main term dominates the error term, then it's positive. So you look at what this is, and let's say you replace this with an x over log x. The size, the conjugacy class cancels out, and then you get you need that x should be bigger than the size of the group squared times log of the script m to the fourth. Okay, that's just from this formula. Okay. But if you can ask a more refined approach, and you can try to improve the here, I'm sorry, the here I had a fourth power of log m, and you can take a more refined approach, and you can in fact prove it with the square of log m. Okay, and now by Minkowski and Hensel, you can replace. Oops, let me see. Now, did I go back? Yeah. By Minkowski and Hensel, you can essentially replace this quantity by log of the discriminant of the top field squared. Yeah, because after all, Minkowski theorem tells you that the discriminant will be bigger than, let's say, for just to understand things easily, k equals q. This will tell you that log of the discriminant is bigger than the size of the Galois group up to a constant. And then similarly, you can get by Hensel, you can get an upper bound involving the primes and the elements of log m. Okay, so basically this is what you get, that x is, as long as x is bigger than some absolute constant times log of the discriminant of the top field squared, there is a prime in this conjugacy class. Okay, so that's a theorem assuming the Riemann hypothesis for Dedekind zeta functions. Unconditionally, there's an estimate like this, as long as x is bigger than some sufficiently large power of the discriminant. So here on the Riemann hypothesis, you have the square of the log of the discriminant, and unconditionally, you have a sufficiently large power of the discriminant. This is proved by Legarius, Podlisko, and Montgomery in 1979. And since then, people have thought a little bit about what is the size of this A. You see, it's very reminiscent of a Linux conjecture type, Linux constant type of problem. So there's a result of Asif Zaman, who was a student of John Friedlander, proved in 2017 that for sufficiently large discriminants, you could take A to be 35. And then more recently, that was improved to 16. And then the question is, these are sufficiently large discriminants, so someone else has figured out what bound force works for all discriminants, but then it's rather large, 12,577. Question that is, I think it is an interesting question. For example, can you prove A less than 1? That would be a very interesting breakthrough, I think, if you could establish that. Okay. So here's the theorem that I want to speak about today. It's a very particular case. So suppose I have an extension of fields L over K that are unramified. Okay, this is unramified. And suppose it's an SN extension. So it's a non-abelian unramified extension. And I'm going to assume Artin's holomorphic conjecture for the so-called hook characters. So I'll say in a moment a little bit about the representation theory of SN, but there are certain special characters of SN. They're called the hook characters. And we just need to know that the Artin L functions, and I'll say what those are also later on, that they're analytic for those particular characters. And suppose I take the class of an n cycle. So as you know, the conjugacy classes in SN are determined by the cycle structure of a permutation. So look at the conjugacy class that corresponds to an n cycle. Then you get the following bound. I don't know if this is, if you can see this. I can magnify this better. Yeah. So I get the discriminant of the top field, and then this exponent, and then some power of the log of the discriminant. Okay, let's look at this power. So remember, this is an SN extension. So the degree of L over K is n factorial. So I'm getting the root discriminant, dl to the 1 over n factorial, and then to a power which is still exponential, but it's exponential in n. Now remember, the degree is n factorial. So this actually is quite small relative to the degree. Okay? But in particular, what we get is a bound for the least prime whose Frobenius conjugacy class is an n cycle, which has an exponent of the discriminant going to 0. remember I just asked you, let's see if I can go back. Can I go back? Yeah, I just asking you here about can I get a less than 1? And what I'm saying is that here we've got a bound in this particular case, which actually goes to 0 as n goes to infinity. Now, just to make sure, tell you that this is not an empty theorem, the results of Froelich that tell us that there are infinitely many unramified SN extensions of a given number field. So there do exist such things. Okay, so that's the theorem that I will try to, let's see if we can, we'll try to, yeah, we'll try to discuss. Okay. Yeah, okay. So let me make some remarks about this. So first remark is that, well, we're looking at n cycles. We can do it for some other conjugacy classes as well. For example, we can do it for n-1 cycles. We can actually get, here you see there's a hypothesis about this unramified thing. You may wonder why we put that in. That's because if you don't put it in, you get a factor that I didn't like very much, involving the ramification. I think it shouldn't be there, but at the moment it is. So if you don't assume anything about the ramification of L over K, you'll get something with the norm of the different of L over K to the power lambda to the n. And remember, this looks like it's exponential, but the degree is n factorial, so this is still small. Now, in the case that it is unramified, of course, what that means is the discriminant of the top field is simply the discriminant of the bottom field raised to the degree. So it's discriminant of k to the n factorial. So another way of stating the bound that I put in the theorem is that there's a prime as soon as you get beyond the discriminant of the bottom field to the power this constant to the n over n to the 3/2 times the power of log dl. Okay. We can generalize this a little bit more. If the ground field is Q, then of course there are no unramified extensions of Q, much less an unramified SN extension. But suppose you had an SN extension of Q, which certainly exist, which is unramified over a quadratic extension of Q. In other words, here is Q over L, this one is Sn, and that there is some quadratic field F such that this part is unramified. Such things do exist, they've been constructed. In that case, yes, then you get a similar theorem that is, again, root discriminant to similar kind of power. And now you actually save something on the bottom of the logarithmic term as well. Okay, again for an n cycle. Now, I just make this comment here again that because the degree is n factorial, this lambda to the n over n to the 3/2 looks exponential, but it's tiny compared to the degree. Okay, so you have something which is, if I want to write it like this, the root discriminant to a power, as small a power as you like of the degree. Okay, and as I said, still it's an interesting problem to try to eliminate this this thing. I would have loved to have a constant here. I don't know yet. We don't know how to do that. Okay. Make sure yes. Okay. Okay. So let's go back and look at the background. Where is this problem kind of coming from? I think there are people in the audience who love the problem, the classical problem of primes in arithmetic progressions, and that's of course the origin of it. So you can consider the classical case where K is Q, and L is the mth cyclotomic field. So then the Galois group is Z mod M star. And this is abelian. So conjugacy classes are singletons. And every conjugacy class therefore corresponds to an element of this Galois group. And the elements of this Galois group are what? If I have an A mod M here, then it's the automorphism that sends the M zeta M to zeta M to the A. That's the and the cyclotomic reciprocity law, which is kind of a tautology, tells you. So what is the reciprocity law? The reciprocity law is the rule by which if I give you a prime P, you tell me what is Frobenius P. Remember, Frobenius P is in general a conjugacy class in the group G. So I give you a prime, and you have to tell me which conjugacy class it is. That will specify a reciprocity law. But in this case, because the group is abelian, I need to tell you an element. Well, which element is it? It's the one that raises, that is A mod M, where P is congruent to A mod M. So the Frobenius E is given by the congruence, the residue class of P mod M. Okay? So therefore, asking, how often Frobenius P is a given element of the group G is the same thing as asking about primes in arithmetic progressions. So this whole problem of Chebatarov is a generalization of the problem of primes in arithmetic progression. So now we've asked what the kind of estimates that we were talking about, the prime of least norm, where Frobenius is a given conjugacy class, is like Linux problem of estimating the least prime in an arithmetic progression. And as you know, there's a beautiful theorem of Linux that says that you only need to go up to a fixed power of the modulus. So if I'm looking for a prime in the arithmetic progression A mod M, I only need to go up to M to some fixed power lambda. And we know a lot about this lambda. For example, Turan observed that if you assume the Riemann hypothesis, anything bigger than 2 will work. So by M squared, you will have gotten all the primes, all the residue classes filled. Now here's something we don't know yet. I don't know even what hypothesis implies it, but Chawla conjectures that 1 plus epsilon should work. In other words, just go past, maybe even M times a small power of log might work, that you should get a prime in every residue class if you go up that high. This is not, as far as I know, this is not a consequence of the Riemann hypothesis. Okay, but now just to compare it with the general kind of theorems we've been talking about before this, if I take this M cyclotomic field, roughly speaking, not exactly, roughly speaking, the discriminant is M to the phi of M. Okay, now you have to worry if, for example, if there are imprimitive characters, you need to take care of that. But in general, sort of morally, if you like, it's like M to the phi of M. So therefore, log of the discriminant is like phi of M log M. And so what Linux is saying is that there's a prime congruent to A mod M, which is as soon as you go to a fixed power of log of the discriminant of this field. Okay, so that should put this into context. Remember what was known? If you in the general case, we know that if you assume the Riemann hypothesis, you could do it when you go up to log of the discriminant of the field squared. And if you don't assume the Riemann hypothesis, you have to go up to some power of the discriminant. Okay, that's the general theorem about primes in conjugacy classes. And that unconditional bound is nowhere near Linux theorem, nowhere near what Linux proved for the abelian case. But because he proved an absolute bound of log of the discriminant, we can't even get a power of the discriminant less than 1. Okay, some years ago, I made a conjecture about these bounds. It still doesn't get us, it still doesn't quite get us, but it gets us closer to Linux theorem. It doesn't get us this close, but it gets us a little closer, namely as a conjecture still. There are absolute constants A and B, so that there's a prime in the conjugacy class C as long as you go up to this bound, namely the root discriminant to a fixed power times the power of the log discriminant. So before, you remember, we just had a power of the discriminant. That's the theorem. I'm asking whether the intermediate thing before getting here is to prove that you could get a power of the root discriminant. And similarly, if the Riemann hypothesis were true, we got that we need to only go up to the square of the log of the discriminant. But I'm asking whether you actually can do better than that, namely 1 over the size of the conjugacy class times log discriminant. Again, in the abelian case, you won't see this because the sign of the conjugacy class is 1. But in the non-abelian case, you will see this. Okay. So just a remark about why this comment here about the size of the conjugacy class I'm trying to say here. The size of the conjugacy class. Let me just make a comment about that. You see, if you think of, here's the group. Let's say this big egg, if you like, egg-like structure is the group, and I've partitioned it into conjugacy classes. Here's a tiny conjugacy class of the identity. And generally, if you have a center, any central element will be a conjugacy class by itself. Right? But in general, you'll have other conjugacy classes, and you partition the group. And sometimes you might have big conjugacy classes, and sometimes you might have medium-sized conjugacy classes, sometimes you might have small conjugacy classes. So here, that's a sort of division of the group. Now, I'm taking primes, and if you think of this like a dartboard, I'm throwing each prime at this dartboard. Okay? then it should make sense that the probability of my hitting a big region should be higher than my probability of hitting a small region, right? And indeed, that's borne out by the Chapoteau density theorem that says there are more primes. The number of primes depends on the size of the conjugacy class as a fraction of the total group. That's true. But in this problem of the least prime in the conjugacy class also, there should be some dependence on the conjugacy class. You shouldn't just get a theorem that says log discriminant to squared or discriminant to an absolute power. There should be some dependence on the conjugacy class, because the heuristic is, if it's a bigger conjugacy class, you'll hit it faster. You know, if you think of you're throwing primes at the dartboard randomly, then you will have a better chance of quickly hitting a large region. Okay, so the bounds should somehow depend on the conjugacy class, and at the moment they don't. That's something to think about. Okay, so and as I said, all of these bounds can be formulated for conjugacy sets and not just conjugacy classes. And so, by the way, sometimes this makes a difference. In some applications, this particular point of view makes a difference. I want to show you one instance where you can actually get exactly what I was asking for. Namely, you can show that the bound gets better as the conjugacy class. So what I did was, some years ago, I took the biggest possible conjugacy set. Namely, just remove the identity element, okay? G minus the identity element. So what does it mean for a Frobenius element to be trivial? It means that the prime splits completely. That's equivalent to this. So therefore, by removing the identity, and I'm asking Frobenius to land in the C, what I'm looking for primes that don't split completely. Okay. Now, if you ask yourself this question, then a long time ago I showed the following, assuming the Riemann hypothesis, that you get a bound like this: log of the discriminant divided by the order of the group whole squared. Okay, in other words, you can find a prime that doesn't split completely, which is as soon as you go beyond log of the discriminant divided by the group whole squared. So this is stronger than the conjecture I was making before here. If I find it. Here, you see, I was making the conjecture that it's 1 over the size of the conjugacy class times log discriminant squared. But in the case of not splitting completely, you get the size squared. Okay, the size of the conjugacy class squared. And the idea of the proof of this, which is different from most of the proofs which go about trying to estimate the least prime in a conjugacy class, it compares logarithmic derivatives of two L functions, zeta functions. One is the Dedekind zeta function of the top field, and one is the Dedekind zeta function of the bottom field. And the idea is that if many primes, small primes of K split completely, then this thing is going to look like the degree, the logarithmic derivative of the zeta function of the top field is going to look like the logarithmic derivative of the zeta function of the bottom field times the degree of the extension. Now, small primes dominate the behavior of this thing, especially near s equals 1. And so if you let this pattern continue for too long, you're going to skew the residue at s equals 1. But both of these have a simple pole at s equals 1 with residue 1. So you make that, what I just said in words precise, and you'll get this bound. Okay, so that's the idea of the proof of that. So that's the only instance where we have a bound really that depends on the size of the conjugacy class, and it's in fact stronger than what I'm conjecturing. Okay. Now, for a general conjugacy class, if you assume not only the Riemann hypothesis, but Artin's holomorphic conjecture, and we'll say a little bit more about that later, then you do get a bound that depends on the size of the conjugacy class on the bottom, exactly of the kind I'm saying. Basically, you have some other decorations here, but basically it's the square of the log discriminant divided by the size of the conjugacy class. So we might ask, what more do I need then if I want to get a bound that really depends on the size of the conjugacy class unconditional? This was assuming Riemann hypothesis and Artin's conjecture. What do I need if I want to do this without the Riemann hypothesis? Maybe I'm still allowing Artin's holomorphic conjecture. What do I need? I need to know the following statements about zero density estimate. So I look at the number of this quantity n sub L sigma t, which is the number of zeros of the Dedekind zeta function, whose real part is between the sigma and 1, and the imaginary part is bounded by t. And you know, just by the usual analytic number theory argument, that this will grow like t log t, and the constant in front is the degree of the top field over 2 pi. So here's the conjecture, also I made in the same paper as the previous conjecture, namely that there's a zero density estimate of this kind, that is the root discriminant times t to the power some lambda, some constant lambda times 1 minus sigma. And I'm not sure, but maybe you need to stick in a logarithmic term also, just to be on the safe side. Okay. Although over Q in general, you get estimates that that don't have a logarithmic term, but then you don't have the root discriminant. Okay. So estimates of this kind, as I said, are known. It is this kind of what I'm conjecturing here. If I replace the root discriminant with the discriminant, these things are known. So what I'm asking you really is about the root, being able to use the root discriminant. The other ingredient that we might need to be able to prove these things, just assuming Orton's conjecture, is a statement about zeros near s equals 1, namely that there's an absolute constant c, so that in this region of basically width and height, degree over log discriminant, there's at most 1 0, and that 0, if it exists, should be real and simple. Again, we know this. If you don't ask for this degree factor, you know that's easy consequence of the functional equation and the Hadamard product formula. So you know 1 minus constant over log discriminant and mod t less than equal to constant over log discriminant is known. So I'm asking, can we add the NL? And that again, that's equivalent. Sort of what I'm saying is replacing the discriminant with the root discriminant. This we don't know yet. But if you had this, then I suspect that you would have most, if not all, the ingredients for proving an unconditional version of an estimate that will involve the size of the conjugacy class. In other words, which will actually get smaller as the conjugacy class gets larger. Okay. Okay. So now let's come to the symmetric group. So symmetric group is, as you know, a set of permutations of 1 to up to n. And you have cycles. So cycles means that I have I1 goes to I2 to IK and then back to I1. And we know that every permutation can be written as a product of cycles. And if you allow the cycles to be disjoint, that's a unique representation. And therefore, you can, for every permutation, you have a unique, this unique product of disjoint cycles. And then you can count the number of 1 cycles, the number of 2 cycles, the number of n cycles. And that gives you a partition of n. So for example, if you have this permutation on 5 letters, 1, 2, 3, 4, 5, that takes 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 5. That's the product of these 2 cycles, 1, 2, 4, 3, and 5. 5 gets fixed. And that gives the decomposition. 5 is 4 plus 1. Here's a 4 cycle and a 1 cycle. Similarly, if I have this permutation, that gives you this write it as product of disjoint cycles. It's these two transpositions, and still 5 is fixed. So that gives the partition 5 is 2 plus 2 plus 1. Two 2 cycles and 1 1 cycle. Okay, so therefore, there's this dictionary between conjugacy classes and partitions of n. So yeah, this point being the cycle structure determines the conjugacy class. In particular, the set of n cycles forms a single conjugacy class. So I have this correspondence of partitions of n, conjugacy classes of the symmetric group, and irreducible representations of the symmetric group. Okay, this last one is just, I mean, for any finite group, I have this correspondence between conjugacy classes and irreducible representations. But let's just make this a little bit more explicit in terms of Young diagram. So if I give a partition P of n, we can look at the associated Young diagram, write the partition as A1, A2 up to AN with the A's in descending order. Then the Young diagram is the one that has m rows. So m is the number of these partitions, elements in the partition. And the ith row will have length AI. So for example, suppose I have the partition 2 plus 2 plus 1 or 5. Then I want 2 rows of length 2 and 1 row of length 1. Okay, this is the Young diagram corresponding to this partition. Okay, so a special subset of Young diagrams. So you see, I can make a lot of these diagrams, but there's a special kind of Young diagram called a hook diagram. And the hook diagram, because they look like hooks, so they correspond to partitions where there's only a single entry not equal to 1. So for example, you write 5 is 4 plus 1, then here there are 4 blocks, and there's a single 1 block here. If you write 5 as 3 plus 1 plus 1, there are 3 blocks, and then a 1 and a 1. Similarly, if I write 2 plus 1 plus 1 plus 1, there are 2 here, and then 1, 1, 1. All of these are examples of hooks. So there's only one entry which is not equal to 1, and the others are all 1s. So I told you that partitions and conjugacy classes and irreducible representations are in one-to-one correspondence. So to each partition, there is a canonical module for the Galois group, a canonical representation space for Sn. It's called the spect module. Just write it as Sp. And its dimension can be computed by the so-called hook length formula. So what the hook length formula tells you is, say, for example, let's look at this example of 5, and I have a partition 3 plus 2. So there are 3 blocks and 2 blocks. So for each block, you look at the number of blocks to the right and below. So here there are 3 plus 1, that's 4. Here there is 1 plus 1 plus 1, so that's 3. And here there's only 1. And here there's only 1, and here there's only 1. So I get this numbering. And then it's just n factorial divided by the product of these numbers. So in this case, 5 factorial divided by 12, which is 10. So this particular Young diagram corresponds to a representation of dimension 10. Okay. So there's a simple formula. And if I had, let's say, 3 plus 1 plus 1, then as you can see, for this one, I have 1, 2, 3, 4, 5. So 5. Here for this one, I just have 2. Here for 1, and here I have 2, and here's 1. So that gives me 5 times 4 is 20. 120 divided by 20, I get 6. So there's a 6-dimensional representation corresponding to this. Okay. So in general, if I have a hook representation, remember a hook representation means a partition rather, which means I have only one non-1 element in the partition, and all the other ones are 1. So right, the Young diagram looks like this. So let's say there are A across and B plus 1 at the top. So A plus B is equal to n. Then by the method I just told you about how to compute the dimensions of the representation given the Young diagram, you'll get that it's basically a formula of this kind, n minus 1 choose B. I might be off by plus or minus 1. I usually make a mistake in these things, but it's roughly like this. You get the idea. If you can compute it for yourself. Okay. And moreover, there's one more point that's important. The character of the representation can be computed by the so-called Mirnahan-Nakayama formula, and it's given like this. It's firstly, the interesting thing: the characters of the symmetric group take only the values 0 and plus minus 1, and so. Sorry, that's not true. No, that's not quite true. But anyway, they're rational valued, they're integer valued. And what you have is a sum of plus or minus 1s going over certain tableau. But for us, if we're looking at n cycles, this the formula, the Mirnahan-Nakayama formula, simplifies to be the following. Namely, if you don't have a hook partition, the value of the character corresponding to, so remember, the partition corresponds to a representation. The representation has a character, namely the trace of the representation. So if that partition is not a hook, then the value of the character on an n cycle is 0. And if it is a hook with R is the unique non-1 entry and the rest are 1s, then the value of the corresponding character on an n cycle is minus 1 to the n minus R. Okay, so these hook representations, the character values are 0 plus minus 1.
What is the sum going over? What's the sum, the t?
Yeah, so you have to,
in the formula?
once you've given the Young diagram for P, you have to divide them into certain sub diagrams. I don't need to define this rim hook, but a certain kind of hook sub diagrams of P. So it's obviously there are terms here. I don't want to go start into. Okay, so but the point, very important point is it's combinatorial. It's completely combinatorial. And also another important point for us is that if I'm looking at an n cycle, the only characters that are not 0 on an n cycle are the hook representations, and they take the value plus minus 1. Okay. Okay. Good. Okay. Now let's look at Art and L functions. So we have, as usual, the L over K group G, and you have a zeta function at the top. It really makes a difference when you can factor the zeta function into L functions, well-defined L functions that behave nicely, because often that means that if you working with these factors, you can prove better theorems than working with the product as a whole. In terms of estimates, what happens is the discriminant, which is the exponential term corresponding to the functional equation of the Dedekind zeta function, gets replaced by some linear combination of Artin conductors, which are the exponential terms corresponding to these LS chi's. So this factorization goes over the irreducible characters of G. And notice, by the way, that each of these L functions appears with a multiplicity chi of 1. Chi of 1 is the degree of chi, the dimension of the representation. Now, the point, of course, is that the reason we have a little bit of a problem in using this factorization, I just said the advantage of having such a factorization. The obstacle is that we don't know the analytic properties of LS chi. We know that it's analytic for real part of S bigger than or equal to 1. It might have a pole at S equals 1 if it's a trivial character. So there's a simple pole if and only if we have a trivial character. Remember, I'm going over irreducible characters. And in general, you have all we know is that we have a meromorphic continuation, but there might be poles. And Artin's holomorphic conjecture is, in fact, there are no other poles, that this is entire apart from a simple pole at S equals 1, which only occurs if chi is a trivial character. Okay. The definition of Art and L functions is generally you don't actually require chi to be an irreducible character to define the L function. And in that case, you would say it's entire apart from a pole at S equals 1 of multiplicity. The multiplicity is the trivial character inside chi, in case chi is not irreducible. Okay, so let's now see if I can give you a rough sketch of how the argument here goes. So just to recall the statement. So I have an unramified extension of number of fields. Galois group is Sn. We're assuming Artin's holomorphic conjecture. Something got erased here. I just need it for the hook characters, for the L functions associated to the hook characters. Now you know what those are. And suppose you take the class of an n cycle. Then there are effective constant, absolute and effective constant lambda mu, so that you can find a prime in the conjugacy class C, as long as you go beyond this power. Okay. So this part of the argument would go about in a sort of more or less standard way. So we want to detect the primes with Frobenius equal to C. So you just define the indicator function. Theta of P will be 1 if the Frobenius is in C and 0 otherwise. You need to worry about prime powers as well. So you can define the Frobenius associated to prime power to be the mth power of the Frobenius of the prime. And you have to also figure out what to do about ramified primes, and what you do, basically you do an average over inertia. You can still define something here. Okay, so then you can, here you consider the Dirichlet series with this indicator, and then log norm of the prime, norm prime to the minus s, summing over prime powers. So this is basically picking up, apart from ramified primes, this is picking up prime powers whose Frobenius is in C. On the other hand, you can write it as a, because by using orthogonality of characters, you can write it as a linear combination weighted by the character values at C of logarithmic derivatives of the Artinel functions. Okay. Notice, by the way, that if I want to do this and then I want to use analytic properties of the Artinel function, I only care if for those chi's for which this is not 0. So in the case that eventually we're going to talk about an n cycle, we only care about knowing, that's why we only care about knowing Artin's conjecture for hook L function. Now, we're trying to detect prime in a short interval. So the short interval in this instance is short interval as short as we can make it at the beginning of the range. In general, you can modify this so that you can detect primes in short intervals at further downrange as well. But there are various functions that are better for that than for counting. These are two different problems, right? One is when you want to count the number of primes. That's one kind of problem. And second is you don't want to count them, you just want to detect their presence. That's a different kind of problem. So for the detecting of the presence, as we know already from the proof of Linux theorem itself, it's good to use a kernel function. So these are various kernel functions that have been used. So we're just using these things that exist in the literature. So if you put, therefore, instead of just taking this to get this thing, it is basically a straight logarithmic, a straight integral rather of this function fc of s. But if you weight it with these kernel functions kj, then you will get what we got here. But instead of norm p to the minus s, you'll get some sort of Mellin transform of the functions kj. And the point here, the why that's important is that this inverse Mellin transform. The inverse Mellin transform is compactly supported. That's why these functions were chosen. K2, I'm going to ignore it basically because this function is used mainly to deal with the so-called exceptional zeros. I'm not even going to discuss exceptional zeros now. So, but when you have to deal with that technicality, this is a better function. But in general, we will just use this one. And as I said, its inverse Mellin transform is looks like this, and it's compactly supported. So when we have this sum here, you see it's going to die as soon as norm p to the m is bigger than x to the fourth. Whereas what is x? X is this parameter that we've introduced. Okay. So you get this, and now, and as I said, we're not doing anything new here. These are the same kernels that Leggeres, Montgomery, and Lisco used, and many other people have used as well. Okay. So now returning to this formula, we have this contour integral. I mean, this notation means I'm integrating on the line 2, FCFS times KGFS. I get this thing. Now we'll move the line of integration to the left. Remember, what is FCFS? FCFS is this linear combination of logarithmic derivatives of L functions, and in particular, we do have chi equals 1 here as well. So at s equals 1, we're going to pick up a pole, and you see the pole of what is going to give you a term like this: C over G K1 of 1. And K1 of 1, what is it? If you look from here and take the derivative, it's going to be log of x squared, the square of log x. So that's the main. When you take this integral and move it to the left, this term, which is basically what I wrote down here, log np times k1 hat of np, where I'm only going over primes of the Frobenius of C, that is equal to this thing. And now when I move this line of integration to the left, I'll pick up a pole at s equals 1 with this residue. And then I'll pick up a term involving zeros. And then I'll pick up a lot of other terms, partly coming from truncating integrals, partly coming from trivial zeros, or partly coming from prime powers, coming from ramified primes, all the nuisance terms that you have to carry. So that's why I just put an inequality here, that it's bigger than or equal to this, which is coming from the residue of this one, minus the contribution from zeros, and then smaller terms. Smaller terms means you still have to work to show that they are smaller, but they are. Okay. Okay. So then you see that what we really need to do is estimate this quantity here, right? Because this is what we had here. This sum here. That's what we need to estimate, and we hopefully will make it smaller than this. Now notice one important thing. This I said is the square of log x. Okay, so that's where there's an x there, and this sum is also dies at x to the fourth. There's no x really. There's no x here, and so we've got to well, there is in K1, I guess, but you'll see now we're going to get an estimate that basically tells us how small x can be. Okay, so we want to estimate this thing, and we obviously need to only consider the chi's for which chi of c is not 0. And in particular, if c is an n cycle, we only need to consider the hook characters. Okay, now to estimate these sum over zeros, you split it up into two parts, depending on how close they are to s equals 1. So whether they're in the unit circle around 1 or they're outside the unit circle. Okay, so the zeros away from 1 is relatively easy to estimate. So I'm going to just ignore those for now. So basically we have to worry about these zeros close to 1. Okay, here now we need an explicit zero-free region that I proved some years ago. So this is sort of the generalization of the old Landau type zero-free region for abelian functions. So it's 1 minus constant over the degree cubed, the degree of the character cubed, times log of the Artin conductor plus the degree of the base field times log t plus 2. Right? In the abelian case, of course, chi of 1 is 1, so this disappears, and log a chi is like log of your modulus. And so this looks like the usual 1 minus constant over log q t plus 2 to 1, that kind of thing. And I allow one possible exceptional 0 if the character is abelian. Okay, so this is a theorem we proved some years ago. And so using this, you get an estimate for this k1 at zeros. And after you put this together, you'll get a sum like this: chi of 1 to the 7th times log of the Artin conductor squared. Okay. The x now here, notice, plays no role. And so now if I put this back into the sum over the irreducible characters, notice I've excluded this. Remember here, I said it's possible there's an exceptional 0. I'm ignoring the exceptional 0 for a moment. It says consider the case where there is no exceptional 0. So I'm summing over non-exceptional zeros here, and I have this kind of bound. Okay. So now if I just partition this, if I partition this, I want to keep chi of 1 with log a chi, and then keep the remainder chi of 1 to the 5th, excuse me, 5th here. Let me see, did I do this correctly? I had a 7, yeah. So I take chi of 1 squared. Sorry, I'll write this as chi of 1 to the 5th times chi of 1 squared. So the chi of 1 to the 5th, just keep it here, and then the chi of 1 squared log a chi squared is less than or equal to this whole sum of this whole thing squared. This is a really crude estimate. So therefore what we need is, if we want the bound to be non-trivial, we need x to be such that log x squared is bigger than this quantity here. The dot 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 means there are other terms that are quite a nuisance, actually, that require a bit of work, but they're not that interesting. So once again, only the hook characters contribute to the sum, and we know that for each r between 1 and n, you have a hook character, which corresponds to this partition, and has roughly this degree, and the value of the character is less than or equal to 1. So this is, you can just replace it by 1, and this is a big deal, you see, because if you look at the usual estimates, the only way general estimate you have for chi of c is chi of 1. And that jacks up these estimates, these powers here, so that's bad. But here, it's being bounded by 1 is a big saving. So anyway, you get n minus 1 or choose r to the 5th times this chi of 1 log a chi squared. Okay. And now there's a simple combinatorial formula that if I take the kth powers of the binomial coefficients, it grows roughly like this. So in particular, the fifth power, I will get it bounded by 2 to the 5n over n squared. And now there's this log a chi, this Artin conductor that we have here, that grows like chi of 1, the degree times the degree of the base field times some stuff coming from ramified primes. And so this chi of 1 log a chi, again, if for a moment, if you ignore the nk, it's roughly this n minus 1 or 2 r squared. So you get 2 to the 2n over root n. And putting all this together, you get that you need log x squared to be bigger than 2 to the 9n over n cubed. So that gives you a bound on x. Now, if I were to, you get a bound like this. Now I've omitted lots of details here. Firstly, remember we said here that the zero is near 1 and the zero is bigger than or equal to 1. Yeah, it's generally true. These are not that problematic, so we can handle that. But then the next thing is, what do you do about the exceptional zero? That is rather problematic. You need to develop a version of the Doering-Halbrun phenomena, and you need one which assuming Artin's conjecture, you can get such a bound, which depends on the Artin conductor, and that's a bit of work, but so that has to be done. And then the last thing is ramified primes and prime powers, which is not so hard to do. But there are quite a bit of details once you get that in order, then bound works. I think the point is that the SN extensions deserve greater attention from the Chevatarov point of view because the representation theory is so explicit. You know quite a bit about it, and I wondered if we could approach these general conjectures from this point of view for SM. Also, the issue of this exceptional zero when it occurs is that we know that for certain classes of groups, yes, there can be an exceptional zero, but if you look at them in some kind of family, they don't propagate. They don't propagate so easily. And so if you're looking at Chevatarov not for just one field, but some family of fields, then it's possible this problem, the exceptional zero, at least in the case of SN, might simply disappear, which is a very important thing if it happens. So I just leave you with this thought that SN extensions deserve greater attention from the Chevatarov point. Thank you for your attention. Once again, Balu, happy birthday, warm best wishes, lots of happiness and mathematical productivity in years to come. Thank you.
Well, thank you for this wonderful talk. Are there any questions, Paul?
I have a question.
Go ahead.
Oh, okay.
Who are you? Who are you? Can you identify yourself?
Sorry for coming in late. I was actually teaching a class and I just got so sorry about that. So slide 24. Can you go to slide 24?
Slide 24.
Yeah. So right there, is it if you were to use Cauchy-Schwarz on the character part, don't you get a saving of don't you get order of the group divided by the size of the class at the very top line? The very top line, that's right there. Yeah. If you use Cauchy-Schwarz, don't you get summation chi of C mod squared over all the characters, and doesn't that give you a saving? Doesn't that give you something like mod G over mod C or something like that?
But the problem is here you get much better because if you see the only characters you need to worry about are the hook characters.
Yeah, why is that? Why are you only
because this formula, this one, that tells you that if I have any partition, okay, the corresponding character on an n cycle is 0 unless you have a hook character.
I see. That's the punchline. Okay, I missed that.
Okay. And on top of that, on hook characters, it's only plus minus 1.
Yeah. Okay.
And there are only n hook characters. Instead of worrying about like you have a group of order n factorial.
Yeah.
You only have n characters. It's tiny, really tiny.
Mm-hmm.
So that's why we focused on n cycles because we could do it.
I see. So if you focus on n cycles, only the hook characters come into play, and then you have an explicit formula for these values, and so you exploit all that. That's
exactly.
That's good.
Exactly. So it's a big deal to say, hey, that this chi of c is just ±1, instead of saying, you know, we've had this problem before, when you try to estimate that what can you do? Yes, you could try to do Cauchy-Schwarz. You can put chi of 1, just becomes too big. And here that doesn't become a problem. And so some of this will work for n-1 cycles too. Ren worked this out in his thesis. You get n-1 cycles as well. And now the question, of course, actually, I think if you were to start imposing like the cycle structure, then you will get some bounds in terms of the number of cycles of different lengths, and so you can vary over all those and see if you get you'll get some bounds.
Very nice. Okay. Thank you. Yeah.
So, are there any other questions?
Okay, I have a quick question. How about, are there other groups besides this symmetric group where you have such simple structure? Some subgroups, I guess they don't contain they're not an AN, I guess. There should be some subgroups, like, do you know others?
We haven't tried. I've not looked so carefully at them. I don't know. I bet there must be. I mean, so far, I don't know people who've looked at it from this point of view, so there might be. I don't know.
Okay.
Yeah.
Thanks.
You're right. If you take AN, it's much more complicated.
Right. Oh yeah. Yeah. AN is the worst case in some ways, and SN is really good. Yes.
Right. And as I said, there's other thing about exceptional zeros not propagating. You know, in SN families of SN fields. So if we develop what we mean by that, then we should see some other improvements as well.
Right. Okay. Thanks.
Other questions, comments, remarks?
You're done? Everyone can go to sleep now.
So if not, we thank you again. We thank the speaker again.
Thank you.